Hello, welcome to the new lecture of this course Transportation Network Analysis. So, in the last class we were discussing about optimization algorithms and we had started to discuss about golden section method, which is one of the interval reduction methods to solve uh, optimization problems when there is a function with single variable. So, this golden section method that we had discussed uses comparison of the zx value at 2 points. Okay, so if you remember in the last lecture we were determining 2 points in the interior of the current interval to evaluate what is the objective function value, and depending upon the relative um, measure we were deciding which interval to discard and so on. So, for objective functions whose derivative can be easily computed, there is another interval reduction method called bisection method. So, we will be discussing that. So, this bisection method uses the fact that the derivative of the function to be minimized, that is dz by dx, is negative for x less than x star and it is positive for x greater than x star when there are no constraints. Okay. So, this is the main idea behind this bisection algorithm. So, this algorithm computes derivative of this function zx at the midpoint of the current interval an comma bn. So, suppose we are at the nth iteration of this interval and the current interval that we have is an comma bn. So, this algorithm will determine the derivative of this function at the middle point, and depending upon whether that is negative or positive, we will be able to kind of decide that the optimal solution should lie in one of the halves of the current interval and therefore the other half can be discarded. So, this is the midpoint of the current interval that we have, that is an plus bn by 2. So, that is being represented by x hat n. So, if x, this derivative of this objective function at x hat n, that is at the middle point of the current iteration, is negative, so then the optimum solution should lie on the right side of this middle point. Okay. So, you can take a look at this diagram here. Suppose we have to minimize this function zx, okay, and the current interval is given by this an and bn here, and this is the middle point of the current interval. So, the optimum solution lies here. Okay. Now, since we are determining the derivative of the objective function at the middle point of the current interval and we find that this derivative is coming out to be negative, so then this interval from an till this middle point x at n, this can be discarded. Okay. And therefore, this next interval will be from this x at n to bn. Okay. On the other hand, if the derivative that we determine at the middle point is positive, then the optimum solution will lie at a value which is less than x at n. Okay. So, then the interval x at n till bn can be discarded. Okay. So, again, I mean, if you show by this diagram here, suppose this is the objective function we are minimizing, okay, and suppose, so this is an, this is bn, okay, and suppose the middle point is somewhere here, an plus bn by 2. So, at this point the slope is positive. Okay. So, then the optimal solution suppose is this x star. So, then there is no point of focusing on this interval which is lying from the middle point till bn. So, therefore, we will be discarding that, and therefore, the next interval will be an comma x at n. Okay. So, one thing that we did not discuss is that what is the reduction ratio of this method, and I hope this is not very difficult to understand. You must have already guessed by now that the reduction ratio should be what? It should be equal to half, because in every iteration we are discarding one half of this current interval before we go to the next interval. Okay, so this is what it is saying. So this reduction ratio is half, as every time the interval is getting reduced by half. Okay. So this bisection method may converge faster than the golden section method, but it requires computation of the derivative of the function. Okay. And this bisection method should only be performed if the computation of derivative of the function is not much more difficult than computing the function itself. So for some objective functions, it can happen that the derivative of that function might be a very complex function. So evaluating that might be computationally burdensome. So in that case, this bisection method will not be a preferable approach. Okay. So in that case, this golden section method might be a better approach. Okay. And one more thing that might arise in the mind is that why we are taking only this half as the interval length. For example, we can also decide to evaluate the derivative of the objective function value at a point, suppose, which is 1/4 distance of the total interval length from the left. Okay. But then the issue is that if suppose while we determine the derivative of the objective function at that point, and we determine that we have to discard the interval from a till this point, which is about 1/4 distance of the total interval from the left, then we will be left with 3/4 of the interval that remains. Okay. So in that case, the number of iterations it might take to reach at a stage where the interval length is very small might become very large. Okay. So to be on the safe side, that is why we are evaluating the derivative of the function at the middle point. Okay. And other than the interval reduction methods, there are other single dimensional algorithms like curve fitting methods and so on. So we are not discussing them here. So these methods can also be used for solving optimization problems that involve objective functions with single variable. Okay. Okay. So until now we were talking about optimization algorithms for functions that have single variable, but now we will be considering the case when we are focusing on optimization algorithms for multivariate problems. Again, just to remind that we are focusing on providing algorithms for those kind of problems which have convex objective function and linear constraints. Okay. So we will be focusing on descent methods. What are these descent methods? Where the objective is to determine a new point x n plus 1. Now here this x n plus 1 is a vector that has capital I components. So x1 n plus 1 is the first component, xi n plus 1 is the last component, and so on. And we want to ensure that this xn plus 1 should be such that the objective function value at this new point is smaller than what was the objective function value at the previous point, assuming of course that we are talking about minimization problems here. Okay. Similar analogy can be applied for maximization problems as well. Okay. So in these kind of descent methods, we will be going to different points of the problem at every step of the algorithm, and we will be proceeding in such a way that the new point where we land is such that the objective function value at that point is lower than what was at the previous point. So at each iteration n, we need to determine this x n plus 1, that is the next point, such that this x n plus 1 is equal to x n plus alpha n times d n. Okay, so here dn is the descent direction vector, okay, and alpha n is a non-negative scalar called move size. So what we are doing here is that we are currently at this point xn, which itself is a vector, okay, because we are focusing on now objective functions that can vary with multiple variables, okay. And here this is a non-negative scalar which is getting multiplied by another vector dn, which represents the descent direction vector, okay. So to give an intuition, what it is saying is that if you are currently at this point xn, we want to determine one, the direction in which we want to go from this xn, and we want to determine how much we want to move in that direction, which is getting determined by this alpha n, okay. So these three things together will be required to determine xn plus 1, okay. So therefore this direction dn is the one in which the function zx is locally decreasing, okay. Why we are writing locally in the bracket? Because when we will be deciding this direction, we will be determining the gradient of the function at the current point xn, okay. So based on that information, we will be making the decisions, okay. So that is why it is being said locally. And then this scalar move size alpha n determines how far along dn the next point xn plus 1 will be, okay. So therefore each component of the variable vector is updated in this form. So this is the same equation, just that now we are writing it component wise. So for each component I here, xi n plus 1 is equal to xi n plus alpha n times din, okay. So it is just the same equation. The previous form that we had seen was the vector form, and this one we are writing component wise, okay, for every component I here, okay. To understand this, let us consider an example here. So suppose we have to minimize this objective function here, okay. And to keep the example simple, let us assume that there are no constraints in this example. Although the algorithm that we will be providing, that will be also be applicable when there are constraints to the problem, okay, because we have seen that the objective is to determine that algorithm that will be able to solve convex objective functions with linear constraints, okay. So suppose this is the objective function here, it is varying with two variables x1 and x2. So here you can see in the diagram here that we have two axes here, x1 and x2 here. Then you see there are various ellipses here or the contours, okay. So each contour is representing those points at which the objective function value is the same, okay. For example, all of the points on this ellipse have the value z equal to 7, okay. That is the objective function value is equal to 7 at all of the points here. Similarly, at all of the points on this ellipse have z equal to 36 and so on, okay. So suppose we are currently at this point 3 comma 1. So your xn, that is at the nth iteration where we are currently at, is this point 3 comma 1, okay, this point. So this is saying the same thing on a contour, the function value is fixed, okay. Now there is one vector here which is showing the direction of the gradient of the objective function at this point, okay. So this is that vector here, okay. And then we have drawn tangent to this vector which is represented by this dashed line here, okay. So all of the arrows that you see here, all of these are possible descent directions, okay. So if we are currently at this point here, then if you go along any of these descent directions, you will be experiencing a reduction in the objective function value, okay. That is why all of these are possible candidates of the descent directions. The question here is that if you are currently at this point xn, then which of these descent directions should we choose, and also how much should you move along in the descent direction that you have chosen to get to the new point xn plus 1. Okay, so that is the main question here. Okay. So this is saying the same thing, this tangent separates the line of descent at xn from the directions of ascent here. Okay, so for example, if this is one descent direction, then exactly opposite to that will be the corresponding ascent direction. Okay, so if you go along this direction, the objective function will increase. But now since the objective is to minimize this objective function, we want to travel along one of these descent directions. Okay. Okay, so it is saying the same thing, several descent directions are shown by dn that emanate from xn, and this gradient direction, a direction of ascent, is also shown by this. Okay. Now note that when you take the dot product of this gradient of z with respect to any of the descent directions, that will be negative, and that is expected because if you will measure this angle between the gradient direction and any of the descent directions here, that will be greater than 90 degree. Okay, so that is why this will always be negative. So in a way, that is the definition of a descent direction. Any direction such that gradient of z dot that direction is negative is a descent direction at that point. Okay. Okay. So here in this discussion, we will be focusing on convex combination methods, as it is an important algorithm to solve multivariate optimization problems. So consider the following program with convex objective function and linear constraints. Suppose we want to minimize this, okay, subject to these. Okay, so here this function zx is a convex function and these are linear constraints. Okay, as you can see that there is summation hij xi and hij are constants and again bj here are constants. Okay, so note that these constraints of the form hij xi, summation hij xi greater than equal to bj can be used to represent non-negativity and linear equality constraints also. And why we are interested in these kind of constraints, because if you remember the optimization formulations of user equilibrium and system optimization have non-negativity and linear equality constraints. So all of those are examples of these kind of constraints, because this is a general form of writing all the linear constraints. So just to emphasize this point again, so if you have non-negativity constraints, for example of this form, this can be represented in this form because bj is equal to 0 in this case here, and hij is equal to 0 for all I not equal to 1 and h1j is equal to 1. Okay. So since there is single term here, so only one of the hij's will be 1 and all the hij's will be 0 in this LHS here. Okay. Similarly, if you have a linear equality constraint of this form, summation gij xi equal to cj, okay, so this can also be represented in this form. How? So we have seen this before also, so we can split this into two inequality constraints. One is summation gij xi greater than equal to cj and the other is summation gij xi less than or equal to cj. Okay, and we can multiply this constraint by -1 on both the sides, so we get this. Okay, so now this is of this form here, where hij is equal to minus gij and bj is equal to minus cj. Okay. So the first step of the convex combinations is to find the descent direction which starts from xn. Okay. So would it always be the best to choose the descent direction as that opposite to the gradient? Okay, so why not just choose that descent direction which is exactly opposite to this gradient direction, okay, which is represented by minus grad z xn. Okay. So the thing is that it may not be always the best choice, because it may not be possible to move significantly in the direction, because there might be some constraint that might be preventing us to do that. So you might reach a point which is infeasible very quickly. Okay. So although this direction, which is just opposite to the gradient direction, offers kind of the steepest decrease, I mean the rate of change of function is the highest, in the sense that highest rate of reduction, but since you may not be able to move sometimes that much in that direction, the overall decrease that you might see in the objective function value may not be the best. Okay. So that is why this direction may not always be the best choice. Okay. However, when there are no constraints, the above direction is widely used, and that algorithm is called the method of steepest descent. Okay. So when there are no constraints, okay, that is, it is an unconstrained optimization problem, then there is no issue and we can decide to move opposite to this gradient direction, because then we will not have an issue that we might reach an infeasible region quickly if we go in that direction. Okay. Thus, the convex combination algorithm looks at the entire feasible region and finds an auxiliary feasible solution yn, again this is a vector, such that the direction from xn to yn provides the maximum drop in the function value. Okay. So in the case when there are constraints, this is not just as simple that we just go directly opposite to the gradient direction, because even though the rate of reduction is highest in the direction, but since we may not be able to move that much in the direction because of the possibility of reaching the infeasible point, therefore we want to find a new point of yn such that if you go from xn to yn, you find the highest reduction in the function value. Okay. Now in the bracket there is something written here, local. Why local is written? Because when we will be trying to determine this new point yn, then we will be taking what is the gradient information at this current point xn. Okay. Now since the objective function value as well as the gradient can change with the different points, so what might be the gradient at this current point xn might not be the same gradient value if you slightly move ahead from that xn and go towards yn. Okay. So that is why this maximal drop in the function value will be the best in local sense. So we will be discussing this more as we will move along. So the direction from xn to any feasible solution y can be represented by y minus xn. Okay. So we want to determine this direction dn, if you recall, when we are trying to find the new point xn plus 1, so that is equal to xn plus alpha n times dn. Okay. Now this direction dn that we are trying to determine, so this new point y that we get, or yn, whichever one we want to use, this minus xn will provide you that direction. Okay. So we are first trying to determine this direction dn, and then later we will come to alpha n. So this direction is represented by this y minus xn. Okay. You can also represent it in form of a unit vector by dividing it with the norm of this vector. So if you do not recall, this notation here, that is norm of v, means the norm of a vector or the length of the vector v. Okay. So it is equal to square root of v dot v. Okay. And that is equal to the square root of the sum of the squared components that are there in the v. Okay. So for example, if suppose this v is having two parts, v1 comma v2, okay, then the norm of this vector v will be equal to v1 square plus v2 square. Okay. So this is that. Okay. So today we will be ending with this discussion here, that the descent direction dn that we want to determine is will be given by this y minus xn here, and this y is that point that we want to determine. Xn we currently know. So, we are currently at xn, we want to determine what y point should we go, so that this y minus xn offers that direction where you encounter the largest decrease in the function value. Okay. And since this may not be having unit length, so this direction can also be considered as a unit vector by dividing it by the norm of that. Okay. So, with this let us end here. Thank you.